material product, try and figure out what things we see within it. So if we go through 1, 2, 3, 4, 5, 6, we got 7 carbons in our starting material, and we have a whole lot more than 7 in our product. Reactivity in the starting material. What do you guys see?
2 electrophilic sites.
Okay. We have electrophilic sites.
Alpha hydrogens.
Okay. And we have the alpha hydrogens located in there. Looking at our final product, it's going to be really hard to tell where all those pieces lined up. We can try and do just longest carbon chains, 1, 2, 3, 4, 5, 6, 7. I mean, we could do something like that, right? But trying to get this carbon and this carbon in the chain to react is kind of unlikely. I would argue looking at that product is really only going to be kind of misleading, is trying to find where it is, okay? Particularly with a hint of me guessing at 11 steps, okay? There's going to be so much going on that trying to work backwards from the product is going to be a bit of a challenge. So I would try and work forwards from the starting material and say with those 2 sites of reactivity, either electrophile or the alpha hydrogens, the alpha hydrogens are probably going to be our best bet because that's going to be chain growing at least, and we for sure need a lot more carbons in our answer. So I would take a look at those alpha hydrogens as our reactivities. If we deprotonated one of those, we'd have a nucleophile, which could be useful because then that could do electrophilic attack, right? Okay. If we did that, that would be 1, 2, 3, 4, 5, 6 carbons. That would get us a 6-carbon ring, which is what we do want in our answer. So that's actually pretty solid, right? Everybody kind of agree with that?
Yeah.
Okay. So if we did that, we're running the Claisen condensation, and we'd be trying to condense that down to our 6-membered ring. Clean up that line a little bit. 1, 2, 3, 4, 5, 6. Sometimes it just needs to be clear for the writer. 2, 3, 4, 5, 6. Position 6 would have the O minus and the O ethyl. Position 1, we continue off, and we'd have the ester out there, right? Okay. That would then come back down, kick out our leaving group, and we'd end with our final product. Can I go ahead and erase the starting material?
Yeah.
Yep. So we'd end with a 6-membered ring. I'm going to do a light rotation on this. We'd have that. Arguably, we've done 1 step. Okay. Could argue this is actually 2 steps because we have to protonate. We have to follow that up with a protonation to ensure that we actually get the Claisen, right? Okay. Now what do you want to try and do?
Can you react it with malonic ester?
Could react it with malonic ester. I don't understand what you mean.
Well, that adds 2 carbons.
So malonic ester would give us 2 carbons, but how? So there's the 2 carbons it would give us, right? How would it give us those 2 carbons? The malonic ester turns this into a nucleophile, which means our structure in red would need to be.
Electrophiles.
Do we have any good electrophiles in that guy? Really?
Did you protonate one of the carbonyls?
Okay, we could protonate one of the carbonyls, and why are you doing that?
To activate the electrophile.
To activate it so that it becomes more electrophilic, but then we can't run the malonic ester because the malonic ester is under basic conditions. What have you got?
You can use first. I literally forgot.
It's okay.
You can change it to an aldehyde. And
Okay.
then after you change it to an aldehyde, you can use the dicuper, the CuLi2 to add more carbons.
Okay. So we've got a suggestion. Turn that down into an aldehyde.
And first, you could actually use just Na. Actually, you could just use NaBH4, so it wouldn't attack the ester. It would just attack the ketone. And then switch that over to.
Okay, so now what you're saying is that we want this to become an alcohol and to leave that as an ester. Why?
I was just trying to get that back to, just a carbon, just a metal.
Was changing the ester to an aldehyde more useful?
I can see that as a possibility, yeah.
That way you could use the copper
And I'll be honest, all I've done is kind of cited this, looked at it as a possibility for ways to go through and do it. The point of this activity is not to get the answer, but to start thinking through the reagents that would allow you to do these steps. Okay. So I kind of liked your initial idea of going to an aldehyde. I'm not sure I understand this
That one was just
process.
extra or whatever. The first one I thought
Going to the aldehyde, I think, is potentially a little bit more promising. And then using Gilman. The Gilman, unfortunately, won't attack the aldehyde or the ketone, so it won't react. So if we backtrack out to your initial suggestion, if we reduce that to the aldehyde, and then try to use the Gilman reagent just to add 2 carbons,
yeah.
2 carbons, so copper. The Gilman reagent is not a strong enough nucleophile to attack either the aldehyde or the ketone. Both of those are null reactions.
So we could just use the lithium with the carbon.
So lithium with the carbon isn't a bad idea. The lithium with the carbon becomes sometimes a bit too unmanageable and could act as a base. So the Grignard's a little bit less base characteristic, so I would argue the Grignard's probably better. If we use the Grignard, what would happen?
You know,
Attack the
1-2
carbonyl.
addition.
Okay, it's going to attack the carbonyl. Which carbonyl?
Both.
Both. Everybody see that? What do you guys think? Useful, not useful? Okay. I would argue that's pretty useful. Okay. If we look at it, we've got these 3 carbons and these 2, so that looks okay. Okay. So if we look at our reagent sequencing there, how do we go from the ester to the aldehyde?
Dibol.
That was our dibol. Again, officially, I think that one has a second step of the H+. So if we added, we're looking up to 4 steps there. We have the Grignard as a step 2, followed by, again, another step of the H+. So there's another 2. Can I erase structures?
So the dibol turns into aldehyde?
That'll take wait, did I do that right? It is ester to aldehyde? Yeah, ester to aldehyde is the dibol. Not alcohol to the aldehyde. Okay, so dibol is doing this very first step in there. So ester to the aldehyde.
It only reacts once.
And it'll only react once. That's the thing that's nice with the dibol. Okay. So can I erase again? To shift this around? There's no way I'm going to be able to fit all of these pieces up here. So we're going to have to constantly cycle through. Okay. Sorry, did you want a picture?
Okay.
It's easy for me to undo. And again, we don't necessarily know that this path is going to work. We also don't know if this is the best path. Okay? The idea is taking a look at what we've got and seeing what we can come up with. Okay? And the hope here is that we think through a lot of these reagents. Okay, so I'm going to redraw that starting material, or a new starting material, but I'm going to turn it. Okay, I'm going to flip it on this axis. I'm going to rotate. Okay, so that way I can see that better. There's my OH. And the OH there, right? Okay, now what? Right, because this is starting to look pretty decent, right?
Still need the methyls.
Still need the methyls.
I have no clue how you put those in.
Well, carbon-carbon bond formation, right? Where do we get carbon-carbon bonds forming from? Enolates. Okay. Problem with enolates right now, can we form any carbonyls? Vigorous shaking of the head is a bit overzealous. We could get a carbonyl here, right? And that would get us enolates. That could get us enolates here or there in blue. That's not particularly useful because
I think I know how we can
I
get
don't want either of those carbons to react. So what do you got, Mustafa?
to make the OH groups a better leaving group, we could use SO6.
So we could convert the OH into a better leaving group, but to do what? So
You need to add something to get it.
to do what? So why are you making it leave? So what we're trying to do is target where we want chemistry to happen. So yes, we can get rid of the leaving group. Okay, and I'm not necessarily saying that that's bad, to get rid of the OH altogether. But again, why? If we look to the final product, yes, it's not there, but we also don't have the methyl groups. To get the methyl groups to attach to the structure, we have to have chemistry in our structure. So if you get rid of the OH groups too early, what might you end up doing? Putting them right back on, right? So if we can limit the removal of reactivity until we're sure we don't need it anymore.
You could reduce the second OH.
Because we haven't heard anything from Alana yet. What do you got?
Can we make an enolate with the hydrogen?
So again, so the enolate has a possibility with that purple area, with that purple oxygen, because we could turn that into a carbonyl, then those blue positions would be our enolates, right? The problem with those blue positions being enolates is, are either of those positions where I want chemistry in my product? No, that would be here and here, and I don't want any chemistry there.
What's
So
the reagent that elongates the carbon chain?
that what?
Elongates the carbon.
So, and that's what I was asking, is what reagents do we have that can add carbons to our structures? Okay, Grignards work with carbonyls. Enolates work with carbonyls. Okay, so we have to consider where that reactivity is located and decide, do we have it there to be able to react or not?
You could make the bottom OH a carbonyl.
The bottom OH is the bottom OH carbonylable. Sorry, it sounded weird, but
Oh, no.
it's a tertiary alcohol. I can't turn that into a carbonyl. Say that again? Can we move the reactivity? Ultimately, we need to move the reactivity, right? Okay, I can't keep it at those two positions. Okay, the alcohols for sure need to disappear, and I need reactivity happening further into the structure. Okay, so how could I possibly move that reactivity? Would a substitution reaction move the reactivity? Would an addition? Could I do an addition?
No,
Why not?
you don't have a pi bond.
Don't have a pi bond. Radicals don't make sense. There's already reactivity in our structure. Okay, so radicals out. Standard acid base is really not moving the chemistry. If anything, it's keeping it at the OHs. So that's not particularly useful either.
You do elimination.
And elimination sounds reasonable. Okay, so what elimination do we want to do?
The bottom OH.
Okay, why do you think we'd eliminate the bottom OH?
Because then we get a pi bond liquid.
We'd get a pi bond. Why would the bottom OH be the most likely to do the elimination with?
Tertiary.
It's a tertiary, okay? So to do that elimination, we have to make that a good leaving group. Okay, this could be an option for the SOCl2. The SOCl2 is going to target the top OH, not the bottom, okay, preferentially, because it's less sterically hindered. Okay, so if we just add acid and try to do an elimination that way, okay, what would happen? So we're putting acid on there, and we're going to do an elimination. What hydrogen am I going to remove to make the pi bond? Give you a hint, there's 3. Which hydrogen do you think we would eliminate?
3.
Why 3?
It'll give you your chemistry and your position.
That gets us the chemistry to where we want it. Just because that's where we want it doesn't mean that's where it's going to go. Okay? Where it's going to go is going to be dependent on what aspect of our elimination reaction. Going all the way back to first semester. It's going to pull 1 because it's going to result in the most substituted double bond. We're going to get a Zaitsev product. Okay? So we would do an elimination, with that hydrogen, forming the pi bond here. So the product we would get out of that.
Could you force the Hoffman?
Forcing the Hoffman becomes a bit tricky. To get the Hoffman elimination, we either need a sterically hindered leaving group, we've got it, and a sterically hindered base. Problem with the sterically hindered base, we don't have a good leaving group if we use a base. So running the Hoffman elimination as we might typically reference it isn't going to work with an OH leaving group. We could convert the OH to a halide, then we could run that. Okay, so that is a possibility. Okay, but that's what we would get if we ran the elimination that way. What do you guys think? Is that useful?
No, not useful.
I feel like we're stuck in a corner.
What if you use BCl3 with the OH?
It would do the same thing as the
So PCl3, we're probably going to get the top OH to substitute out as a chloride first. So what we're discussing is potentially running the elimination the other direction or with the other OH. Okay. Which is going to be difficult because they're both OHs. But we could possibly get an elimination there. But yeah, it does feel kind of like we're getting boxed into a corner. That would react there. What I see from this structure is the potential for an alpha beta unsaturated ketone. Problem with that is that that still doesn't put the chemistry anywhere where we want it, right?
like with the initial structure, it would have been a lot easier to put the methyls on there.
So you're saying as awesome as we liked this path, we don't like where it went.
Yeah, I mean, if we put the methyls on there before, then we could do the glazer and be in a much better spot.
There's an interesting idea. So I think undoing as slowly as I'm doing it is not going to work. So you're saying to put the methyls on right out of the gate
Yeah.
with that? Okay, how are you going to do that?
I don't think you can.
Yeah,
Because you can't run the Claisen if you don't have the second acidic hydrogen.
you would need that second acidic hydrogen, but if you only put one methyl on, wouldn't you have the other side available?
Yeah.
Yeah, the issue that I'm going to see here is that that hydrogen isn't particularly acidic right out of the gate. Right, Okay, remember the Claisen wasn't likely to run with that first acid-base step. I don't know that you're actually going to be able to remove that hydrogen and put the methyl on easily. Okay, we can just say it and do it for the hell of it. Why not? You guys want to try that? Do you have any better ideas? What's that? I don't think it's a good option. But again, this is more an activity of trying to think about the reagents in those pieces. We can discuss and say that's not likely to happen, but hey, it's the best bet we've got. I think doing the Claisen first is probably the best bet. That's my 2 cents. We got a couple new people in. What do you guys see?
Assuming that we're going to lose both F oxides, we're going to have to throw on 6 more. No. Yeah. You have to throw on 6 more carbons. So
And just ignore me.
we'll have to do that thing that we were on Wednesday, the harbor acetoacetic.
So that has been a suggestion to try and run something with the acetoacetic.
Because we're going to have to add 6 carbons on here. And since we can't have more than 2 carbons.
But you aren't adding them all at the same time. So I'm not sure why I see adding 6 carbons as a number is a good idea.
Well, in between, in all of our steps, we're going from, assuming that we're losing both F oxides, you're going from 7 carbons to 13 carbons. So you need 6 more coming in. That means stuff like lithium cuprate.
Yeah, well, no, we're definitely talking about carbon sources. That's the question, is what carbon sources do we use? If we look at Mohammed's suggestion, we're hoping to put the methyl on and then do the Claisen. Sorry, stop.
I thought I missed something. What happened when I was gone?
Everything begins with M.
It's all good. My name is close to that.
No, it's not.
My last name is Ahmed.
If it makes you feel better, there was a Muhammad in past classes that suggested things and that was very active, and so it's a good reference, but it was totally inappropriate. I apologize for that. If we go with Mustafa's suggestion, we've got this. The other option is trying to go back to that Claisen, right? And our Claisen result outright is just this. So we got blue versus red, right? The red at least has another methyl on there.
Can we try an intramolecular allyl? Religion carbon.
You mean like a Claisen reaction?
Okay. Yeah.
That's what we just did. That's the intramolecular.
Okay.
And I do really think blue is going to be the better step because I don't think red's going to work. Okay. But I'm fine with working with either. What do you guys see?
Could you put one methyl on because you have an acidic hydrogen?
Where's an acidic hydrogen?
At the alpha position to the ketone.
So I have 2 alphas to the ketone.
The bottom one.
Okay. The issue with targeting the bottom one is what? So red versus purple. What's the issue between red and purple?
Red's more acidic.
Red's going to be vastly more acidic. So if you want to target the purple, you're going to have to neutralize that red acidity first.
Can you do two equivalents?
To equivalence, you're still going to have that red one acting as your base or your nucleophile first.
You can reduce away.
Could you reduce it down to an alcohol?
Reduce what to an alcohol?
The ester?
How do we reduce the ester to an alcohol?
LAH.
So LAH will absolutely reduce the ester to an alcohol,
Also,
Yeah, you don't want that.
but it also does the ketone. Right? Is that what you want?
what happens if you use diball again?
The diball will take the ester to an aldehyde. So are we focusing on the blue one? Because I think the red one won't work. I could be wrong too, so.
I just realized the red one, you really just need to throw on methyl.
Yeah.
If you can get.
Yeah, it is actually very, very nice looking, but I don't think the red one works.
You wouldn't be able to get to it.
I don't think you can selectively get that single methyl on there, because I don't think your ester is acidic enough to deprotonate to get that. So we want to try diball again?
If we use like BR2 or something like that, where would the bromine?
So the BR2, what you're referencing is the rough equivalent of the haloform. Okay, so we run it under acidic conditions because we don't want to explode this thing. It's going to go where that most acidic hydrogen is. You're going to put the bromine in at that position. What's that?
Move it and then turn it into a methyl.
Gives you a good leading group.
You'd have a good leaving group, and you're talking about moving it. If you, we can't move the bromine, but we could run in a reaction where we've moved the chemistry.
Do an elimination.
We could do an elimination. Where would we eliminate if we put the bromine on there? So this was diball and the BR2 and acid.
If you eliminate the bromine,
Where would the elimination occur? Where's there a hydrogen to remove?
The next to the left.
To the left.
then you could use the copper, the double copper one for the 1,4.
Okay. Now we do have that 1,4 alpha beta unsaturated carbonyl, right? Okay, and officially actually both directions. We've got that 1,4. So we could now pull off a copper reagent. Okay, what do you want to put in there?
Methyl.
You just want a methyl? Okay. So there's a methyl.
Actually, before you do that, could you put another bromine on the bottom one?
Why?
Because if you just did that, then we really go back to the acidic hydrogen over there.
So your thought is before we do the carbon, we rerun the BR2 in acid? The hope is that what happens?
That on the bottom most alpha hydrogen, you pull that out.
That is an acidic alpha hydrogen, so you could put the bromine on there. Yeah.
And you could eliminate that again.
Okay. I'm gonna need to backtrack a lot, sorry. You'd be eliminating out here.
Now you have two of those.
Now we have two 1,4s. Let's look at where that chemistry is gonna put us though.
The 4 is at a different position.
You see that? And that doesn't quite align with what we want here. I'm not saying that's a bad idea, but I would see that chemistry being shifted off. I'd be a little bit careful about doing that, and I would probably leave the bromine on there. Okay. Why might I leave the bromine there?
Substitution.
Could try and just do a direct substitution at that position. Okay. That would be my thought, but that seems pretty reasonable. I kind of like that idea. Does everybody track that?
Yeah.
Okay. So that means we'd be looking at that material. And now what do we want to try and do?
Put the methyl on the top one.
Okay, we want the methyl on the top one. How are we getting the methyl on the top one?
Copper lithium.
Okay. Our CH3 copper lithium reagent. I don't think that reacts with the halide, so we'll be okay there. We should be putting the CH3 up there. We've got, whoops, bromine down here.
Can we do CH3 MgBr now? Next step.
What's in each?
The CH3 MgBr.
What's in?
That'll attack the carbonyls.
Yeah.
That's going to attack both carbonyls. It-
Does it prefer the bromine?
No. Grignards actually don't do substitution well. And unfortunately, I think Gilman's actually do, but I'm choosing to selectively ignore that for the moment because this looks somewhat promising. So if we did the CH3 MgBr, that becomes problematic because we'd put a methyl in the wrong spot.
Right, so let's make that CH2, CH3 MgBr.
If we did CH2, CH3, that would put on our methyls, right? CH3, CH2. There's one of our ethyls with an OH. There's the second of our ethyls. That was a CH3, and this is a bromine. We still have that OH.
How do you substitute out the bromine?
Could you do LiCH3 for the substitution?
And that becomes the question is how do we get a carbon nucleophile there? LiCH3, I think, is actually going to preferentially act as a base and do an elimination.
Can you, what's that, like, that crazy triphenylphosphine,
Yeah.
like, that whole big ring
The
with,
That was doing a Vidig.
yeah, can you use the OH? I can't remember how that one works, I'm drawing a blank, but I think the Vidig would make that circular and drops one off. I can't remember.
So the Vidig attacks carbonyls.
Oh, right.
The problem that we're going to get here is that you're trying to make a Vidig with a secondary halide, which would work, probably poorly. The carbonyl you would react it with would be formaldehyde. So that, I mean, in the pure hypothetical system that we're working in, that could work.
Let's turn this into, oh, hell on this, magnesium solid in there. Let's take this and turn it into a,
So you're saying turn that into a carbon nucleophile
yes.
so that it can attack a carbonyl, formaldehyde. That'd work. Problem with that as a Grignard right now is why?
It's really, really big.
It's big. Oh, you have acidic hydrogens.
We have acidic hydrogens within that structure, so we'd have to solve the acidic hydrogens first.
So let's reduce away the oxygens.
How do you reduce away the alcohols?
Alcohols.
Chromic acid.
No.
Chromic acid oxidizes.
Oh,
Is something that's going to, we have tertiary and
I mean,
secondary.
you could go through and say chromic acid, this top one, to a carbonyl, and then you could use your Clemenson, I was about to call it Claisen, the Clemenson, to reduce that one off. So I could see that working. But that other OH is going to become tricky.
What if we get rid of that first one? So we do the Clemenson, kill that
Right.
one.
So our suggestion is to go through and run the Clemenson. Our oxidation first. Oxidize it to the ketone.
And
Now we run the Clemenson. That'll knock that off.
now we will add magnesium solid in a basic solution. So you'll pull Mg.
I understand where you're going with that.
Is this still considered water necessary to kill it?
Because it's internal, I think that's going to be a problem.
Okay.
How can we reduce away an alcohol?
We put a strong oxidizing agent, like both.
The strong oxidizing agent isn't going to oxidize that oxygen because there's no hydrogens to remove at that position. We need hydrogens here. So reducing the alcohol we don't have ability for. What if we turn the alcohol into something else? Carbonyl we couldn't do because there's no hydrogens there.
MSCO.
That would be turning it into a leaving group.
did you turn in,
Well, if we turn it into a leaving group, then no shit. Don't worry.
What reactions could happen if that was a leaving group?
substitution, elimination,
What was the second one?
elimination,
If you eliminated it, what would it turn into?
carbon, or a double bond?
A pi bond, right? Can you reduce a pi bond?
Yes.
What can you reduce a pi bond with? He said yes. It's okay.
Hydrogen and
Hydrogen and a metal. So we could reduce that with platinum and H2. That would reduce away the alcohol. Once the alcohol is gone, now we have no more acidic hydrogens. So now what could we do?
Now you can make
Now we could run that Grignard reaction. Ugh.
Ask this question.
Right. No. And so again, the point behind this is not to come up with an answer, because if it was to come up with an answer, I did a really crappy job doing this because we didn't show all of those answers. But what we were trying to do is think about how we're breaking through it. Let's try this path. What would that result in? That was a dead end. Let's try this path. What happened there? That was a dead end. If I did this, what would it, if I want this, how could I possibly do that? Let's try this reaction or this reaction. And notice we referenced the reaction types as well as the reagents to complete them. We talked about substitution, elimination, additions. We're using those terms to think about what reactions, because that can help us classify the reagents. Does that make sense? Okay. That's how you should be thinking about synthesis. Not just, oh, I need to do this step. You don't know you need to do the step. Okay. What you need to be able to think about is what are the pieces that you've got to move through it. Kind of, sort of? Okay.
Is it all multiple choice on
ACS is all multiple choice. And so they're never going to ask an 11-step synthesis because you get 4 multiple choice answers. Right? What they're probably asking about is what's the proper sequence of reagents. The sequence of those reagents comes into a lot of play in the 4th unit. Okay, the unit we haven't talked about yet, because they do lots of synthesis things there, and it opens paths and closes paths depending on which way you go relatively quickly. The paths opening and closing were 2 or 3 steps down the road. So it was very hard to be able to piece those things out, right? But again, the idea behind this activity here was pulling at what those reagents are. Well, what could we do? This is what I want to do. What things do something like that? That's what I want you to be thinking about. Does that make sense? Should we try an easier one? Yeah? So, from the practice exam, where'd we go? Over there. How could we possibly do this? So what do we see within this one?
You're breaking open your ring.
Okay, breaking open the ring. I would argue there's something else that you're seeing before that that allows you to say we're just breaking open the ring. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I don't have to make any carbon-carbon bonds, but I am going to have to break some carbon-carbon bonds. Okay? So that, I would say, yes, we need to be breaking open the ring. Okay? So how could I break open the ring? Okay? In this case, I'm going to say it's breaking open there. It doesn't really matter whether I pick 2, 3, or 2, 7, but 2, 7 for me is naturally easier to see. Okay? To break open a ring, how can I do that? Okay. There's a suggestion for permanganate. Okay. If we look beginning to end, yes, there's a ring opening. Okay, so that's huge. What else happened? Formed 2 carbonyls. I would take that a little bit less specific.
Oxidized 3 times.
You increased oxygen. Oxygen. Yeah? Okay. So, oxidative cleavage. What reagent does oxidative cleavage? KMNO4, ozone. And we went oxidative, so H2O2. Okay. Cool. To do that, what do those reagents react with? Do they react with alkanes?
Yes. Alkenes.
Alkenes. Okay, which means I need a pi bond in my starting material. Do I have that? No. So what do I need to do? Make a pi bond. Okay, that pi bond needs to happen internal to the ring. To do an elimination, I need a leaving group. Do I have a leaving group?
No, bad one.
I have a bad one. Okay, so I have to make it better. How do I choose to make it better?
You protonate it.
Okay, I could just protonate it. Okay, if I want to do an elimination, I need to make sure I protonate that with the minimum amount of nucleophile. Okay, so I could get more specific on that H+.
H2SO4.
H2SO4 is probably a good option. Okay, I'm also breaking open, or not breaking open the ring yet. I'm trying to break a carbon-hydrogen bond. How easy is that?
No.
Not easy, so I could add some heat. The H2SO4 makes a good leaving group. The leaving group can leave. I form that tertiary carbocation. That heat can help break that carbon-hydrogen bond. And I'd have my pi bond. Make sense? Right? There are other ways to do it, yes. Right? This tends to be the easiest one that people jump on. That's fine. Okay? Now I want to oxidatively cleave. Should I oxidatively cleave yet?
Yes.
Just like with the other one, we don't really know, so what should we do?
Try it.
Try it and see what happens. Okay? So let's do our oxidative cleavage. I'm just going to do the KMNO4 because it's easier to write out. Though officially I should be adding a little bit more details. We'll deal with that in a second. Okay? If we oxidatively cleave, we stretch that pi bond and we turn them into oxygens, right? You're like, God, that looks awful, Mike. You're right. It does look awful. 1, 2, 3, 4, 5, 6, 7 carbons. So I'm going to redraw that. 1, 2, 3, 4, 5, 6, 7 carbons. Carbonyl, carbonyl. What's the issue about that last position? It should turn into the carboxylic acid because there's still hydrogens to pull off, and I ran under oxidative conditions with permanganate. I could have switched it to ozone, and ozone with DMS as step 2 would have been an aldehyde, not a carboxylic acid. Which one do I want?
The carboxylic acid.
Okay, why do I want the carboxylic acid?
SOCl2 and
You can use pieces straight.
Slow down. To make that jump, that's now just the conversion of the carboxylic acid to the acid chloride. I don't have an ability to go from the aldehyde to the chloride, but the acid to the chloride I do with SOCl2. I think we can do it with PCl3, but SOCl2 tends to be the most common referenced. Okay? Yes? Mustafa? This is an or.
So, you just put, it's supposed to be a carboxylic acid in the ring?
Not in the ring, but when we cleave that, I intentionally just did the cleavage and then noted afterwards that we do have that hydrogen there. Because of that hydrogen, under oxidative conditions, we would have to turn that into an OH. Okay? So it was progressing into those pieces. Does that make sense?
Yeah.
Okay. If you're being asked for a synthesis on the ACS, this is fair game for the ACS, and this is something that they could go through and ask. If we looked at our answer choices, and this is going to get a bit messy, but I'll just draw A. They could say A1, H2SO4, delta, 2, KMNO4, hot, concentrated, 3, SOCl2. What do they say for B? 1, H2SO4, delta, 2, SOCl2, 3, KMNO4, hot, concentrated. Does that make sense? Okay. So you're taking the same reagents, but they're switching up the order. Does the order matter?
Yes.
Yeah, it's critical behind it. That's how it worked. Okay. So you'll see a repetition of those reagents. One of the other things that they could throw on for this particular one is that instead of saying hot concentrated, they could have said
Cold dilute.
cold dilute. Will cold dilute work? No. So now officially the question isn't asking about synthesis, it's asking about permanganate as a reagent. What does the permanganate do? They've just changed the framework by which they've asked the question, but it's now still asking just a permanganate question. Does that make sense? And does that get to what you were asking about, Milana? Kind of with what you would see on a multiple choice. You'd ask about multiple choice with synthesis.
Oh, well, in my mind, I was like, this right here, it took like 30 minutes, so like.
And so on a multiple choice test, you would see these answers listed out. Okay, so you aren't going to have to go back and be like, well, what the hell reagent should I use? You'll have one. And you can start with that and say, what would that do? Okay, it's still the same process. Some of those steps get shortened a little bit because the reagents are now listed out for you. And because there isn't a huge variability in those reagents, usually you can just say, okay, H2SO4 in heat does this. Would that be productive? Okay, yeah, that's productive. Or no, it's not. Does that make sense?
Yeah.
Sound reasonable? Should we hit you with another one?
We do the other one.
Yeah.
Nice.
I am not creative. That question that's up there came from my not creativity, and I'm pretty sure it doesn't work.
Thanks.
I'm just telling you where it came from. Okay. What I want you to think about is the pieces, and that's where that's useful.
oh, this one.
And this is one that I would accept a few different answers for. So, what do you see? What are the changes? Pi bonds disappeared, and I have an H2.
You need to add H and OH, and you need to add H to the least.
Okay, so I'm hearing a suggestion moving forward, so I'm going to guess you're going from the starting material.
Yeah, starting material.
And you want to add H and OH.
Yes, across the pi bond with the H in the anti-hydrogen. I want the
Okay.
H on the. Yeah.
And you want the OH like that. Okay? If it's a synthesis, you've shown evidence of what you want. That's good. You should show that. Officially, that's not really, really good because it's a synthesis. What are you being asked for? You're being asked for the reagent, not for that intermediate. But drawing that intermediate product might give you some hints about what to do for the next sequences. So you may not even know how to do that step, but you've at least established something that can get you points. That's useful.
H2O and THF.
Okay. So what is the reagent that adds H and OH? BH3 and THF, followed by OH, sodium hydroxide, and H2O2. I think it's actually flipped, H2O2 and hydroxide. Right? So some of that memorization is useful. If you just memorize, oh, that's going to do THF. No, not at all. THF doesn't do that. But when do you see THF? With the boron reagent. So having aspects of information memorized can be useful because it is a multiple choice test. You can see those pieces there. Does that make sense? So you can take advantage of that. Yes?
Can we now write Gabriel synthesis using
Okay. So we're now hearing a suggestion for a Gabriel synthesis. Okay. Depending on how much you've memorized, you probably saw that at the very beginning. Like if you, the whole point of Gabriel is what? Primary amines. That's what I have at the end. So Gabriel's a really good idea. Okay. So what is the first step of the Gabriel synthesis? Let's see what you've got memorized.
You add acid to the.
You add KOH with
Oxides. Ethanol.
with that monster so that you can remove the hydrogen, making that nitrogen what?
Electrophilic.
Try again. Making it a nucleophile. So that it reacts with what in step 2?
An alkyl halide.
An alkyl what?
Halide.
An alkyl halide. Typically, something with a bromine. We don't have a bromine. Okay? So, what could you go through and do? Would it work with the alcohol? Probably not, because while it is a nucleophile, it is also a base, and that base would likely target that hydrogen, nullifying your leaving group ability. So could we convert the OH into a leaving group, like a halide?
SOCO2.
We could run something like SOCl2. That would turn that into a chloride. Chloride versus bromide, fair. Okay? So that's now our step 2. And then step 3 is
KOH again.
KOH again. And what does that KOH do?
Nucleophilic attack.
The nucleophilic attack that cleaves all of that. Getting us to our final product. Okay? Everybody look at it and go, that's perfectly clear and understandable. So laughter, meaning you don't think that's perfectly clear and understandable. That's what I would expect to grade, and I would accept that for full credit. Okay? I expect to see a mess. Okay? What I'm piecing through is, do you have the logic to understand what's going on with that? I'm not looking for, do you have perfection? I'm looking for, do you understand where those pieces are and how they move? Does that make sense? What do you got, Rob?
Would we have to necessarily memorize the structure if we just write Gabriel synthesis with the KOH?
Good point. So can I delete all this?
Yeah.
Okay. I do want you to remember the left half before the Gabriel, because we're going to, oh, fine. I lied. I'm not going to delete it all. I'm just going to delete this part. So could you have written what's on the left half and then said, then,
Should be fair game. I mean, it's a name reaction for a reason.
yes. Majority of the points. All becomes questionable. You've proven you understand a sizable amount of that. You're definitely putting me in a tight spot to say no. Okay. So I would bet if you gave me all of that information that yes, I would give you full credit. Does that make sense?
When you're using the SSCL2, can you use still BCL3? I'm sorry.
PCL3 would also do it.
Could you use QBR3?
Yes.
Okay.
Is this the best synthesis?
No.
No, in fact, this one has too many steps.
Could you reduce the alcohol to a carbonyl?
I was thinking you needed an alcohol, which is why I said I wanted to make it an alcohol. I was thinking that you were using ethanol.
The alcohol was a complete red herring. You didn't need the alcohol at all.
Yeah. You just, yeah, roar.
And now our Gabriel stuff. For those of you that don't know how to spell, I don't know how to spell Gabriel either. I don't know. It is E instead of A? Okay. Well, no. Is it I-E or I-A for?
It's
I-
IE.
It is I-E.
L.
It may not be like church Gabriel. Like, be careful on that. Just so you know. Just because that's how I freaking remembered the stupid thing doesn't mean that's how it's spelled. Okay? So we could have done the roar process first. That is a better answer. Depending on who you have for an instructor, some people would say that first one we drew up is wrong because it's not the best answer. Did you get there? Okay. I'll accept it. Okay. Make sense? Okay. Before we answer other random questions, I'm going to real quickly, like if I take longer than 5 minutes, you can stop me. Look at these last remaining slides about some protein structure. Okay. The main thing that I want to get at or show and point to, which is going to take more than 5 minutes probably, is looking at this peptide. Okay. This peptide, is relevant because what we have here is an organic compound that was made in those red sections. Okay, those are amide bonds. If we look at the amino acids, what we did was took a carboxylic acid and combined it with an amine. So if we were going to do the reverse reaction, we're talking about an addition elimination, a nucleophilic addition. The nitrogen comes in and attacks. We break the pi bond. There's our nucleophilic addition, followed by the elimination of OH. Is hydroxide a good leaving group? No. In fact, it's a horrible leaving group, and this mechanism does not, or this reaction does not work very efficiently.
That's why you got
Okay. That's why in synthesis, what we'll go through and do is a couple things. We could up the equivalence of the amine. Okay, that becomes very challenging in this case because the amine and the acid are tied to each other. Okay, so I can't up the equivalent of just the amine.
You could put
Okay.
I
I could try and add another base, an alternate base to scrounge the hydrogen instead of the nitrogen, so that's a possibility. In lab, what we can do is up the temperature. We could also change the activity of the acid by turning it into an acid chloride. As soon as that's an acid chloride, the nitrogen will naturally attack very, very quickly. Okay? So typically when we talk about this kind of reaction, we're using acid chlorides because they're more electrophilic and it would initiate the formation of the amide very, very swiftly and efficiently. So swiftly that all you have to do is layer the two materials and you've formed that polymer immediately. Okay, right at that interface. And we'll see that for those people in lab. Okay? The other thing that's important here is that we're adding a whole bunch of these units. Okay? So we could reference this as many units and one unit. Okay? So if we take apart many units, we can get one unit. If we take one unit and we put it with a bunch of other units, we get many units. Okay? Referring to these compounds as many units when one unit is kind of dumb. So what did we do? We refer to these as poly to reference the many, followed by mer being an individual unit, and mono referencing one, and again, the mer referencing a single unit. Okay? Kind of neat. It is a language breakdown. Okay? And that's what we're looking at. What makes this even more interesting and challenging is that you're now bringing in the concept of polymers. Polymers are a challenging concept to deal with. We will have a flash video discussion on polymers for those of you not in the lab. For those of you in the lab, we'll actually talk about polymers in a little bit more detail. There are two types of polymers as far as you're concerned. Condensation polymers and addition polymers. Okay? Addition polymers, as the name suggests, involve addition reactions. What kind of reaction was this?
Addition polymer.
This was a nucleophilic addition, but then an elimination. So it doesn't quite fit the addition category. Where else have we seen addition reactions? Unit 1. Unit 1 was our primary section for addition reactions. Officially, Unit 2 did nucleophile additions. Okay, but in Unit 1, we talked about additions, and those were with alkenes. So when we're thinking about addition polymers, you're looking at alkenes as the monomer unit. When we look at condensation polymers, you're looking at the elimination of a small molecule. That small molecule is typically water. So when I run a condensation polymerization, I heat it up because that's not an easy bond to break, but I heat it up and form water. What does the water do when I'm in a hot solution? It evaporates, turns into a gas. Usually the glassware above the reaction isn't being hot or heated, so it cools. What happens to that hot liquid? It condenses, and I see a condensation. So they're referred to as condensation polymerizations. To run the condensation polymerization, I needed to be able to do a nucleophilic addition and the elimination of that small molecule. So to do a condensation polymerization, what functional group do I need to see in my monomer? Not necessarily a carboxylic acid, but the carbonyl. The carbonyl is the crux of that. Okay? The acid part doesn't necessarily have to happen with a condensation polymerization. When we're talking about that, it's the elimination of a small molecule. Where it was classically discovered was when the elimination of that small molecule was water, but it does not have to be water. All of the nucleophilic addition eliminations eliminate a small molecule. Some of them eliminate water. Most do not. Okay? So if you're asked for a condensation polymerization, look for a carbonyl. You're now doing a condensation. If you're being asked for an addition polymerization, look for an alkene. Does that make sense? Okay. So where this is coming from is protein structure. When we study biochemistry, we need to disassemble our proteins to determine what sequences made them, because with that sequence, sometimes we can learn something about function. Okay? So when someone's learning how to build a car or make a car run, what do they sometimes do? They tear all the pieces apart, and then they can put it all back together later.
With the blower ability.
Okay? With better parts. Okay? The same thing's happening in biochemistry. We want to study by taking them all apart. So how could we take it apart? We're breaking it at that acid derivative bond, because that's the weakest bond. How we do that gets varying names. So one is the Edman degradation. Okay? How does it happen? You use a special reagent. That special reagent helps to initiate a cascade of reactions that takes it apart. Okay? It is neat. It is interesting. It is also not super critical to you surviving through this class, and so I don't want it to distract you too much. Okay? But your textbook does talk about it. If you're interested in biochemistry as a field, you should read through it. If you're interested in medicine as a field, skim it. If you don't care, then don't worry about it. Okay? But there is some interesting things in there. Okay? Yeah, and I'll leave it at that. So with that, right, because there's just a bunch more synthesis and stuff, taking it apart, putting it together, we'll go ahead and call the slideshow done, and we'll move to your questions.
The first question on the exam, the old exam, was you don't have you're supposed to...
Practice exam, yeah.
Practice exam.
Oh.
You're lacking a spike at 1700 and a single mass spike at, or maybe it's the second question?
Yeah, it's third question, but that's, no one's counting. Okay. It says, a student attempted the following reaction with the acid workup to get the product. In their analysis, the IR, no peak at 1700. Carbon NMR, same deal, no peak, but at 200. Okay, no peak. Okay. Part A, clearly identify to what the IR and carbon NMR signals correspond. So this is strictly spectroscopy. We don't even care about the reaction. What does it mean if I don't have a peak at 1700?
There's no carbon.
Okay. There is no carbon-oxygen double bond. Okay. What does it mean if I have no signal at 200 ppms? It means the exact same thing. Okay. There is no carbonyl in your product. Okay. They're both saying the exact same piece of information. Okay. So then it says provide a mechanism given the following detail. Sorry for the slightly twisted looking structure.
So you're going to attack twice.
Okay, so we have the Grignard, and it said that this was what they expected to get. Did they get it? No. Okay. The evidence up here says that this structure is not true. Okay. And really by not true, it's not so much not true, it's not obtained. Okay, at the end of the experiment. Okay? So let's go back to our starting material and say, well, what happens? What's the most reactive thing?
Your carbon nucleophile.
The carbon nucleophile with your Grignard. So what does it do? Attacks the carbonyl. Because we asked for a mechanism, we need to show this in gory detail. We're going to break the pi bond first. And by gory detail, we can cheat and draw pHs. That is okay.
Oh, thank you.
Okay. It could be misleading. You'll notice I've got what appears to be 2 dashes. This is typically why I circle charges. Okay. With multiple colors, it can also be useful to go through and show the lone pairs. Okay. Is this a stable structure? So what happens? The electrons come back down. We kick out the leaving group. right?
But
Isn't that the expected product?
It's gonna react again.
Okay, so that could be problematic. You already have a hint, though. You've just addressed that that product is not obtained. That does not mean this reaction doesn't happen, but it does mean you should be critically evaluating each step of this process. Did you address the negative carbon appropriately? Was there any other positive it could have gone to? Looking through our initial steps of our mechanism. No. Negative oxygen? No, we reform. Like, that's fairly clear. What did I form as a product?
A carbonyl.
A carbonyl. But wait, what did the Grignard attack?
A carbonyl.
A carbonyl. So that's interesting. I'm starting with an ester, and I end with a ketone. Is there a difference in reactivity between those?
Yeah, it's more reactive.
The ketone is much more reactive than the ester, which means the instant the ketone is formed,
It reacts again.
more equivalents come in and attack.
Aren't they kind of like on the same level?
As far as reactivity, no.
It's like right above it.
It is actually significantly above it as far as reactivity goes. So we get the second attack, we get a negative oxygen. Is there a leaving group now?
No.
No. So what happens?
Acids
Protonate
like
the oxygen.
The reaction stalls until we add the acid workup. And we would end with the final product. Does that final product have a carbonyl? No. Does that support the spectroscopy evidence?
Yes.
Yes, you're now done. Okay. As far as reactivity between the ketone and the ester, you might go like, well, I don't remember that reactivity. So this is one of the things, I'm going to yank this from you, sorry, that is sometimes built into our exams. If you have the exam, or if you don't have it, you can go back and reference it later, and you can take a look at question number 16. Which of the following reactions will have the highest concentration of products? We have the ester, aldehyde, and ketone. If the ester, aldehyde, and ketone are all the same reactivity, what would our product have been here?
The carbonyl.
It would have stopped at the carbonyl. Okay. There were questions in the multiple choice to help push you in case you missed something, to get you a little bit further with the mechanism. So if you don't know an entire mechanism and you can't support everything, that's fine. Just get as far as you can, continue on with the test. Double back after you finish the test. Some of those pieces may fall into place because the exam sometimes has Easter eggs to help try and push that information back at you.
So, I didn't go this way, so but I found that, I was looking online, it says that metal cations can stabilize the hemiacetal. And I was wondering if that NGBr can stabilize the O negative, and then when you do your acid workup, you get a hemiacetal, or is that like a spontaneous?
So let's say it stabilizes the O negative.
Yeah.
What did it do to the carbon positive?
Well, the carbon positive kills itself on the carbonyl. So you
On-
get basically the first step.
Okay. So you're saying here, that first step is what you're saying?
And then the NGBr stabilizes the negative, like the M plus.
I think I see what you're saying there.
'Cause I
It's
looked
not
at it and it's
significant.
Okay.
No. Okay.
It'll
Yeah.
just reform the carbonyl at such high
Yeah.
yields that, okay.
Yeah.
And the two phenyl groups.
And at best, what would happen? It stabilizes the hemiacetal, you add acid, you form the hemiacetal, and now what does it do?
Oh, then it goes back.
It goes back to the carbonyl. You should have seen spectroscopic evidence of it. You did not.
Okay.
So, no. Was that your question? I forget.
Yeah, that was my question.
So, because that one had a part C on it.
It's the multiple reasons why.
provide an explanation for why the IR and carbon NMR signals are missing. Okay? So, the ketone was more reactive than the ester. That's the absolute best answer. Okay? There are multiple explanations here.
There's strong, stupidly strong nucleophiles.
Okay, we could go with stupidly strong nucleophiles that will continue to react with the ketone. What if you didn't know that the ketone continued to react with the Grignard?
There's a massive amount of resonance in there. Like,
Not necessary. Let's just say you could get to that ketone, but you didn't know anything else. Okay, but you do know that IR signals are missing.
That's one of the rules of the Grignard.
So you should know it again from the Grignard, but let's say you don't know that. How could you answer C? You'd get stuck, right? What do you know has to happen to that product?
You lose the carbonyl.
The carbonyl has to disappear somehow, which means that structure, whatever that product is, did something. What did it do? Kept reacting. Why? Because the ketone's more active than the ester. Do you have to say that? You could just say it kept reacting. Something destroyed the carbonyl. Okay? That is an acceptable explanation. You have taken the evidence to say this thing has been destroyed, but your knowledge isn't enough to explain why. Don't worry about that part. Focus on the part of knowing that you know that something else had to happen. You just don't know what it is. So, David, your explanation of it formed a hemiacetal. Okay? Wrong, yes. Does it prove the carbonyl disappeared? Yes. That's an acceptable explanation for that answer. Okay? So, big, vague questions, purge. Purge whatever you know. Okay? They're being written vaguely so that you can get some form of points with minimal effort. That's why they're being written. It's not just me writing vague questions. Okay? Or if it wasn't intentional, purge whatever you know so that you can then come back and be like, but I put something down and you wrote a crappy question. Either way, you get more points. Okay? So I'm going to